Buongiorno! This is an Algebra 1 video. It is Chapter 7, Section 3. And today we are discussing rational exponents. So to get started here, the easiest thing to do is probably to show you how to do all this stuff by example. Sometimes the description or the definitions can get kind of technical. So even though I have it up on the board for you to read, I want to rest assured to help you understand that it'll get a little bit easier as you see the examples. So, for any non-negative real number, so we're talking about numbers that are real, they're not imaginary, and non-negative means that they're positive or 0. So if it had said for any positive real number, then that wouldn't include 0 as an option. So when it says non-negative, it means that it could be positive or 0. So for any non-negative real number, which we'll call b, when you write b to the 1/2 power, it's the same thing as writing the square root of b. You probably didn't know that. And you can actually check really simply with your calculator. We know that the square root of 4 equals 2, but according to this, instead of writing square root of 4, I could write 4 to the 1/2 power. So what I want you to do is on your calculator, I want you to try that so that you can see how it works. So there is a button on your calculator that we call a caret key. So I want you to type on your calculator TI 4, and then there's this little button that looks like that. We call it the caret key. It basically raises the number to a power. And so that button is on the far right hand side of the calculator underneath the button that says clear. So you use that button, and then you use your parentheses, which are to the left of your division button. And so you put a parentheses 1 divided by 2 close parentheses, which is basically saying 4 to the 1/2 power. And when you hit enter, you will get the answer 2, which is the same as the square root of 4, which is 2. So that's just there to kind of demonstrate to you that it's the same thing. So in our examples, it says write each expression in radical form, or if it's in radical form, they want us to write it in exponential form. So this is the exponential form where you see the exponent, and this is the radical form where you see the square root, which we'll call a radical. So for 25 to the 1/2 power, that would be the same thing as saying square root of 25. Now they're not asking us to actually figure out what the square root of 25 is, but they're asking us to write each expression in radical form. Now, if we wanted to, we could keep going, and yes, the square root of 25 would eventually equal 5. In the case of b, it's the square root of 18, and that means they want us to write 18 to the 1/2 power. And since there is no perfect square root of 18, we're just going to leave it like that, 18 to the 1/2 power. In part C, I want to make a special note here that the 5 and the x are not both being affected by the 1/2 power. Only the x is being affected by the 1/2 power. If they had wanted you to put the 1/2 to both of them, they would have had to use parentheses, and then the property of multiplication would have applied from yesterday's lesson, where they would both get the 1/2. But since there are no parentheses, we are to assume that the 5 is on its own, and x to the 1/2 power would be the same thing as the square root of x. So your answer would be 5 times the square root of x. Now in part D, since the 8 and the p are both underneath the square root, then that does mean that when we write out the exponential form, we want both the 8 and the p to have the exponent of 1/2, which would be 8p to the 1/2. And then that's how you do that. So now if you will try example or do it yourself number 1, we will move on to the nth root concept over here. So the next concept or theorem that we have for rational exponents is for any real numbers, a and b, and any positive integer n. So in this case, it's saying positive integer n. That means that it can't be 0 and it can't be negative. It's only positive integer n. If a to the n power equals b, then we call a the nth root of b. So So again, that might sound kind of technical, but we're going to try to use that concept here in the examples. So because 3 to the third power is 27, so we have 3 times 3 times 3, so 3 times 3 is 9, 9 times 3 is 27. So because 3 to the third power is 27, then 3 is considered the third root of 27, so, or the cubed root of 27. So what they want us to have here is, they're asking us what the cubed root of 27 is. Well, I just told you that if the cubed root of 20, since 3 to the third power is 27, then the cubed root of 27 is 3. Okay, it's kind of like saying the square root of 36 is 6 because 6 squared, or 6 times 6, is 36. So it's like the same thing. The cubed root of 27 is 3 because 3 times 3 times 3 is 27. So what we're looking for in part B is a number that multiplies by itself 5 times, that's a fifth root, 5 times, to get 32. Well, that number happens to be 2. 2 to the fifth power is 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32. So 2 to the fifth power is 32. Therefore, the fifth root of 32 is 2. Alrighty, so now you can try to do it yourself, number 2, and it's here on the same board. And then we'll go on to our next example. So here we go with more properties. For any positive real number b and any integer n greater than 1, so now we want our n to be greater than 1. We don't want it to be a negative integer, we don't want it to be 0, so it's got to be greater than 1. When you write b to the 1 over n power, that's equal to the nth root of b. So now we already knew from before, the first property, that b to the 1/2 equal square root b. Well, the thing is that we don't normally write a square root. We don't put the 2 in there, but technically there's a 2 there. It's the same concept behind writing x to the 1 power. No one writes x to the 1 power. If there's no exponent present, we assume that it's x to the 1 power. Same thing like when you write x plus 3. There's no number in front of the x technically, but we know that that's 1x. We don't write the 1, but it's actually there. So same thing here. We don't write the 2, but we assume that it's a 2 because a square root is the smallest form of a root that we have. But then what happens when you have a cubed root or a fourth root or a fifth root? Then things start getting crazy. So we're just kind of amplifying our notation here to include not just square roots, but cubed roots and fourth roots and sixth roots and all kinds of roots. So basically, what they're telling us is that whatever the little number is here in the radical, outside the radical, that's the number that goes in the bottom of this fraction. All right, so we've got b to the 1 over n this time. So in the case of the 1/2, it would be a square root. If it says 1/3, it'll be a cubed root. If it says 1/5, it'll be a fifth root, and on the story goes. So for 125, they want us to simplify this, and it's 125 to the 1/3. And so what we know is that it's going to be the cubed root of 125, and then like the previous example, we're looking for a number that multiplies by itself 3 times to get 125. So 5 times 5 is 25, and 25 times 5 is 125. So because 5 to the third power is 125, the cubed root of 125 is going to be equal to 5. So for example 3, we now have our answer that that it's 5. Over here, very similar situation. We want to put the fourth root of 1296. So we want a number that multiplies by itself 4 times to get 1,296. So that number is going to be 6. 6 times 6 is 36, and 36 times 6 is 216, and 216 times 6 is 1296. So 6 to the 4th power equals 1296. Therefore, the fourth root of 1,296 is 6. All right? So for example 3, we get 6 for part B. All right, and so now you can try to do yourself number 3. And then we're going to go to our next example, example 4. And I believe there are 5 examples, so we're almost done. It says, for any positive real number b, and any integers m and n greater than 1, then b to the m over n power equals the nth root of b to the mth power, or the nth root of b to the m power. So basically, we keep graduating to the next level. In the previous example, the m on top was always a 1. But now we're going to allow for even, we're going to expand even further. So now you don't necessarily always have to have 1/2 or 1/3 or 1/4. It could be any fraction. And by the way, that's why this lesson was called rational exponents. A rational number is any number that can be written as a fraction. So basically what's happening here is that we have all of these expressions that have exponents that are now fractions. So we started off with the easy ones like 1/2, and then we did 1/4 and 1/5 and 1/3. But now what if the top isn't a 1? So we have examples here where you have 2/3, 3/2. So basically the bottom number is still consistent with what we had before. The bottom number of the fraction is the number that goes on the little house, the little radical. The top number of the fraction is the number that goes basically on the inside, so b to the m power. So this is one way, this is the most common way of writing it, the nth root of b to the m power. But you can also write it like this, where you put the m out here, and it's going to have the same effect. So we're going to see how that works out. So in example 4, we have to simplify 64 to the 2/3 power. So we can rewrite this as, so in this case, b would be 64. And since the bottom number is a 3, that means that we want the cubed root of 64. And then according to this notation, I can put the top number, the 2, on the outside. If I do that, now I can probably deal with the inside portion of this first. I need a number that multiplies by itself 3 times to get 64. So we know that 8 times 8 is 64, but that's not going to work because the number has to multiply by itself 3 times, not 2 times. So what if we try 4 instead? 4 times 4 is 16, and then 16 times 4 is 64. So because 4 to the 3rd power equals 64, it means that the cubed root of 64 is actually 4. So now we put the 4 in there, and then we square that, because after we do the inside portion, we still have to square that, and our final answer is 16 for example 4. So then we come to part B and do the same kind of idea. We're going to go with B is 36. And the bottom number of the fraction is a 2. And so it's going to be a square root. So we can write the 2 in, or we can just leave it there and assume that it's a 2. I'm going to go ahead and write it in. And then we're going to put the top number, which is the 3, outside. So we're going to put the 3 up here. And then we're going to deal with the square root of 36. I think we all already know. We're looking for a number that multiplies by itself twice to get 36. And I'm sure we all know that number is 6. The square root of 36 is 6. So now we're going to replace the square root of 36 with 6. And then cube that. And 6 times 6 is 36. And 36 times 6 is 216. So now that simplifies to 216. And that takes care of that before. So now we're going to let you do these do-it-yourself questions here on the bottom. And then we're going to go to our last example and call it a day. So our last example states, for any real number b greater than 0, so this time b has to be bigger than 0, but it can't be 1. So it has to be bigger than 0, so it can be like 1/2, but it can't be 1. So what it's saying here is that if you have the same base, b to the x, equivalent to b to the y, that these two things will only be equal to each other if and only if. So when you see that double F there, I'm not misspelling the word if. It's not pronounced if, okay? It's abbreviation for the phrase if and only if, which basically means that this is a biconditional statement. It means that you can say b to the x equals b to the y if x equals y, and you can say x equals y if b to the x equals b to the y. So you can say it in both directions. We call that a biconditional statement. And when you do that, you can abbreviate that with IFF, which means if and only if. So this is literally saying b to the x will equal b to the y if and only if x equals y. So our goal here is when we have our expressions, we need to have the same base. They both have the base b. In our examples, we don't have that right now. But what we need to do is rewrite our equations so that they actually do have the same, they have to have the same base. So that would be 6 to the x. And is there another way that we can write 216 as a base of 6 instead of 216? And yes, we just saw earlier that 6 to the third power was 216. So instead of writing 6 to the x equals 216, we can write 6 to the x equals 6 cubed. And now we have the same base. So these two expressions will only be equal to each other if their exponents are equal to each other. So very plainly, we know that x equals 3. And that's how we solve the equation there. X just equals 3. All right. We want to do the same thing over here, only this time we have a 5 on this side, which is 5 to the 1 power. And over here we don't have a base of 5, but we know that 25 is 5 squared. So we can write, instead of 25, 5 squared, and then that's to the x minus 1 power, and then 5 to the 1. But we still don't quite have the same base, because this is 5 squared and this is 5. But we learned in our previous lesson that when you have a power raised to a power, that you can multiply the exponents. So then we can write 5 to the 2x minus 2. So 2 times x is 2x, 2 times negative 1 is negative 2, equals 5 to the 1. So now we do have the same base, and so these two expressions will only be equal to each other if their exponents are equal to each other. So that means that I can take 2x minus 2, which is the exponent of the left, and equate that with 1, which is the exponent on the right, and then solve for x. So 2x equals 3. Divide by 2. In this case, x equals 3 halves. So that is how you solve an equation that has an exponential in it. And so now I will let you do these, a couple of examples. And once you have completed this do-it-yourself question, you will have completed your notes for this lesson. And I will see you in class, and thank you for watching.